vectors. So I'm going to look this week at scalar and vector quantities. Scalars are quantities that are entirely defined by a single numerical value. Examples of scalar quantities include time, i.e. the time taken for the tank or water, etc. Temperature of an oven, mass, scale, speed of a vehicle in meters per second, scale. Vector quantities, on the other hand, are defined by more than just their size. They've got both a magnitude, which is their size, and a direction. Examples of vector quantities: velocity, the velocity of a car, 90 kilometers per hour, due west. Notice that it's got similar units to speed: meters per second, a length over time; kilometers per hour, a length over time. If the direction is important, it's called velocity. Force, a force of 60 newtons applied at an angle of 60 degrees. Horizontal. Acceleration, the velocity of a projectile increases at 2 meters per second squared in a vertical direction. Yeah? So we've been looking at how we can look at quantities that are effectively vectors. Second slide, are these vector or scalar? A temperature of 70 degrees, P or S. 5 meters cubed of volume. Get a downward force of 20 newtons. The vector. Joules of work of the scalar. That's the scalar. So if the specification includes a direction in either degrees or the points on a compass or up, down, you're looking at that. So, notation used to represent vectors. We need to distinguish between vector and scalar quantities by using different notation for vectors. You'll find a number of different conventions used in textbooks and online that include using bold print for vectors. An arrow across the top, so it's a vector between point A and point B, where point A is the starting point and point B is the end point of the vector. An arrow, or a simple line across the top, vector between A and B, or just vector A with a line over the top, and lastly having an underlined letter. Now, for the benefit of what we're going to do, I would suggest that we stick as far as possible with the first or the fourth option. If you're typing your work up, it's quite easy to make it bold. It's also reasonably easy to underline, and you can underline in handwritten stuff as well. You should be distinguishing in your work what are vector quantities and what are scalar quantities with one of those two methods. Alright. I haven't anything against you using these two if you're using the formula system of putting your maths into Word. Find those additions in there. So there's nothing against that, but please make sure that you show which quantities are scalar and which quantities are vectors with one of these. So, representing vectors by drawing. We have already had a little bit of a look at this in science, and so a vector quantity can be represented graphically by a line drawn, so that the length of the line denotes the magnitude of the quantity, and the direction of the line denotes the direction in which the vector acts. Now, an arrow is used to denote the sense or direction of the vector. The end of the arrow vector is called the nose. So this is the nose up here where the arrow is, and the starting point is the tail. For example, so that's a force of 9 newtons acting from base to the top. Yeah, all fairly simple. Yeah, I hope. So we can, and we've already had in science, but we can add 2 or more vectors together by drawing. This assumes that you have the required equipment. It's attained by drawing. I will make a remark there that where that part of the temperature part of science claims that you're measuring the angle to 100 degrees and not really you're only going to measure to one vector. So if you're asked to do that in this line, you need to draw as big as you can fit on the plane. You must state what the scale is, and you must only record results that you can actually read from measuring the length of the line with a ruler and measuring the angle. So you're going to be able to measure the angle to about half a degree's accuracy and the length of the line to the nearest half a millimetre, which you've then got to apply your scale to. Right? Drawing a sketch, not a scale, is always useful in being able to just visualise the problem and what the result, the approximate result of adding those vectors together or what you're going to do. That way you can identify if you've made a mistake with a positive or negative sign in your calculation of making all this out. Right, so it's worthwhile being able to draw sketches. We can deploy 2 methods for this. Firstly, the nose to tail method. So if we're going to add these 2 vectors, F1 and F2, at an angle theta, we draw F1 along its horizontal line from O to A, and then we draw F2 up from the end nose of F1. We draw the tail of F2 up at 45 degrees and complete the triangle. Yeah. And that way, that's a good one for measuring. You've got a nice long line there. We can measure this angle. Well, we can see where the result we're expecting is a positive angle for the result vector supposed to be. Right, so that's nose to tail method. The second method is the one you've already seen me do, which is the parallelogram method. Yeah. And in that way, we draw the 2 vectors as dashed lines. So this line here is parallel with that one. That's what that means. That one parallel with that one. That one parallel with that one. So completing a parallelogram, and then the resultant vector is up the middle. Okay, and we're looking at the angle. Pull it out in there. Yeah. So, and if we want to do a trigonometrical method of finding the length of that line and this angle, this angle here, because that's a parallelogram, and that angle has to be equal. So that angle in there is half of whatever theta is for a start. So that gives you a start with that. And these 2 angles that must also equal alpha as well. That must be equal, and therefore you've got quite a bit of information there before you start. All right. So graphically, there are the two methods: nose to tail, and the parallelogram method. My personal preference is for the parallelogram method, although nose to tail is quite useful if you're adding more than two vectors together, because you just keep going off the end of the. So if you've got to do three, you go draw the first one, second one off the first one, third one off the fourth one, and put the result in. So if you had three boxes, you might go like that for the first one, up there for the second one, down there for the third one. And results in there. So for more than two, nose to tail method is quite useful. Okay, so that's by draw. So we're going to look at now, and we've also done a little bit of this maybe in a different way, but resolving vectors into horizontal and vertical components. Force vector F is shown in figure 5 at an angle of theta to the horizontal. Such vectors can be resolved into separate horizontal and vertical components. Right, so if we construct this right angle triangle over here, then O to A is the horizontal component of F, and AB is called the vertical component of F. So this is the horizontal, and that's the vertical. And using trigonometry on the next page, we can find those two vertical components. So the horizontal component, OA, can be found using the cosine. Cosine of this angle is OA over F, hypotenuse. We can rearrange that to OA is equal to F, cos of the angle. So the horizontal component is always the magnitude of the vector multiplied by the cosine of the angle, and the vertical component is just the sine function. Alternatively, once we've found one of the two horizontal vertical components, we could use Pythagoras' theorem to find the other one. So there's an alternative there, or there's a check. And where there's two methods, it's always useful remembering that one is a check of the other. Yeah? All okay so far? Right, problem 1. Resolve the force vector 50 newtons at angle 35 degrees to a horizontal and vertical component. So there's two problems here, 1 and 2, for you to have a go at now. Alright? Alright gents, that's the problem. So how do we calculate the horizontal component? So what you done then? Just a click. Oh, okay, yeah. Cos 35 is equal to yep. the answer is yep. And the vertical component, sine. Fifty sine 35, which is so that 50 newtons at 35 degrees is made up from a horizontal force 40.96 and a vertical force of 28.67. Right, second problem. Another 5 minutes and I'm going to pick someone to come put their answer up on the board. So what you should notice from that is just a couple of things. Always the degree symbol. If you've got a negative sign, put brackets around it. If you've got more than one thing in the cosine, sine or tan function, just confirm that that's not cos minus 30, which doesn't mean anything really, but it's a cosine of minus 30 degrees. Yeah. Sine of minus 30 degrees. All right. What else is, so yeah, if you're going to use this labeling system, that would have to be O. You'd call that A, and then Macaulay's call this V for the vertical component. Right? Doesn't matter what you call them, right? As long as what you use as labels on your diagram is what you use in your maths. Right? Yeah. Right. So addition of vectors by we have two vectors f1 and f2 at different angles. We can sum them together, add them together using the horizontal and vertical components. So we've got f1 that's got a horizontal component f1 cos theta 1. That's this distance here. And we've got a horizontal component for f2, which is f2 cos theta 2 here. Yeah. And then we've got two vertical components with the sine functions. Okay. We can add them together, firstly, by calculating the total horizontal component. So that's like saying we're going to go nose to tail with these two components. There's the horizontal component of f1. There's the horizontal component of f2. We add those two together, and we get the total. Yeah. And then we add together the two vertical components. So vertical component of f1, for instance, and the vertical component of f2 on there. Effectively what we're doing is add them together horizontal components and vertical components. So when we've got V and H, capital, we call them, okay, and what we can do then is we can draw a right angle triangle using the total horizontal component and the total vertical component, and we've got a resultant and an angle in the corner. So since we have H and V, the result of F1 plus F2 is obtained using Pythagoras theorem. So we can find the length of the hypotenuse, the length of the resultant from H squared plus V squared, and taking the square root of it. And we can find the angle using the tan function, tan to the -1 of V over H. Yeah. So that's the method for finding a resultant by adding the vertical and horizontal components separately. Alright. On the next page, there's result of the displacement vector of 40 meters at an angle of 120 degrees in horizontal. Yeah. Force of 5 at an angle of 45 degrees. The second force of 8 newtons. Both forces acting at a point. Calculate the resultant. And the 8 newtons, usually calculate the angle with respect to 0. Not always. But so have a go at that one, please. Consider a volunteer. So that's what we do. We want to add two vectors together using the horizontal and vertical components. Find the horizontal components by adding two horizontal components together. Add the two vertical components together. Turn them into a right angle triangle problem. Use Pythagoras to find the length of the hypotenuse, result magnitude, and -1 find the angle. And the angle could equally be radians if that's appropriate for the problem. Alright? Right then, let's just go through this problem and the final answer, because it is a little bit tricky. Right. You should have, I'm not going to go through all the detail, you should have a total horizontal component of -5.829. Maybe slightly different, depending on how much you're angular. Yeah? And you should have a total vertical component of 21.12, and they're both meters per second. Yeah. Okay. So you might have slightly different depending on your rounding and how many significant figures you use, but in that sense, that's irrelevant. So your resultant is equal to the square root of these two numbers squared and added together. You should have got 21.191 meters per second, or quite close to that, again depending on your other figures. Okay. What's more important is if we now draw the right angle triangle made up of those components. So we've got a total vertical component of A0 minus 5.829. So it's negative direction that way. Yeah, negative horizontal direction. We've got a vertical component of 21.12 meters per second. Okay. Now our resultant, we complete the parallelogram, goes in here, and there's our right angle triangle, of course, right? I can put minus on if you like, so doesn't really make a difference. Okay. The important thing to remember is that this green vector here has got to be specified as length of line, which we've calculated to be 21.91 meters. 91 meters. And we're interested in this angle from 0. But when we do our trigonometry, we're going to find this angle, called alpha. Yep. So therefore, we say alpha is equal to tan to the minus 1 of 21.12 over 5.839, and that comes out at, if you put negative sign in there, it comes out at minus 74.6 degrees. Yeah. Alright, and why I say that's minus is because it's in this quadrant, it's gone from here round clockwise. So, the magnitude of that angle is 74.6 degrees. Therefore, the angle we're looking for is 180 minus 74.6 equals 105.4 degrees. So this whole vector resultant is the 21.91 meters per second, angle 105.4 degrees. That shows you the importance of drawing that diagram and drawing it and taking notice of positive and negative signs in the two horizontal vertical component vectors. Alright? So, moving on from that, you'll be pleased to know that we can do these vector calculations using complex numbers. Okay. So we can two force vectors F1 and F2 shown in the figure. F1's at an angle of theta 1, F2 at an angle theta 2. So a similar situation to the problem we just did. Alright. Horizontal and vertical components. You can use your calculator to convert the two forces in a rectangular form. So we can do polar conversion from F1 at angle theta 1 converted to H1 plus V1J. So it's a horizontal and vertical components. What we've just been doing, those calculations you've just been doing, is what your calculator does when it's converting from either polar to horizontal and vertical, or back the other one. Okay, and then we can resolve the second force by converting to rectangle. So this conversion here is the rect conversion that we looked at last week, the week before. Yeah. So results can then be found by adding together the two horizontal components and the two vertical components, and then converting back polar to get the answer. Okay, now going to look at the doing what you did as problem 4 earlier in the same way, doing it this way. So we'll do this one, and then you can do the 3-course one that you've just done to finish off, and there's a couple of extra problems for you to have a go at as well. Okay, so what we've got here is we've got a force of 5 newtons at an angle of 45 degrees from a force of 8 newtons. Yeah. So this problem is, we'll call it the result R is equal to 8 angle 0 degrees plus 5 angle 45 degrees. So if we say 8 angle 0 degrees, convert that to rectangular, and 5 angle 45 degrees, convert that to rectangular. The 8 angle 0 is 8 plus j. Can you remember how to do that conversion on your calculator? You push shift and then rec, which is on the plus minus or somewhere down in that area. Yeah, that opens a pair of brackets. You put in 5 and then you put shift, and then I think that's the closed bracket. Give you a little comma, and then you put in 45, making sure your calculator is in degrees, and then you push close the what do you get? 3.536 I got here. I'll put that, alright. And your J part is 536. If you think about it, a 45 degree angle must have an equal vertical and horizontal part. And that's J on here. Yeah. So we've got to add those two together. How do we do rectangular addition? Add the J parts and do them separately. So we add the two, add these two parts, 8 and 3.5, so it must be 11.536 plus, and that's 0 plus 3.536 J. And then we convert back. So we go 11.536 plus 3.536 J, convert the polar, equals. Now I've got 12.07, make sure you get this answer, and that'll be newtons, angle 17.04. No, we're not multiplying. you end up with the j squared when you multiply, Rogan. Yeah. So, addition of rectangular numbers, we add all the real parts together separately, add all the imaginary parts together separately. And have you check that conversion, please? Make sure got it right. And if you check back to the earlier problem, where you've done 8 newtons and 5 newtons, you should see we've got the same answer. You tell me which way you think's the easiest. I know which way I think's the easiest. Alright, you've got the same answer. So, please have a go at problem 7, which is the 3 velocities you just done the manual way. Have a go at doing them by converting their polar values to rectangular, adding them together, and getting an answer. You ain't been and bought that Casio calculator yet then, Taylor?